All right, greetings everyone. The purpose of this video is to go over an example of finding all zeros of a polynomial. And by all zeros, we mean both the real and the complex zeros of the polynomial, or any of those that exist. So let's take a look at this problem here. So we're given the function f of x equals 2x to the fourth plus x cubed minus 9x squared plus 16x minus 6. And again, we're going to find all zeros, whether or not they're real or complex, of this polynomial. Now, to get us started, since the degree of this function we see is 4, since the highest power we see in this expanded form is 4, none of the techniques we know for solving this directly will work. So we can't factor this, especially because if we look at all of the terms here, they don't all have something in common other than that they're all divisible by 1. And we also can't use something like the quadratic formula. So to start, what we're going to do is graph this function and find one of the zeros using the graph. So I'm going to go ahead and switch to a screen here where on Desmos, I have graphed this function. It's these purple lines, and I know we can't see the whole function, but we do see where it crosses the horizontal axis. We see 2 points, in fact, where that occurs. One being right here and the other being here. And so to figure out what the coordinates of those are, we just need to pick one of those. I'm going to go ahead and click. And I can see that this one left here is -3, 0. So that I know that -3 is one of the zeros of this function. So with that information, what I will do is go back to my problem here. And since I know that -3 is a zero of this polynomial, I'm going to perform synthetic division using that zero. So I'm going to put -3 here in a box. I'm going to list out the coefficients of each term here in the polynomial. So the 2, 1, -9, +16, and -6, and then perform my synthetic division. So I will bring down the 2. It will not change. And then I'll multiply that by -3, which will give us -6. Add that to the 1 to get -5. Multiply that by -3, which gives us +15. Plus the -9, that'll give us +6 times -3, gives us a -18. +16 plus -18 is -2. Times the -3 gives us +6. When that's combined with the -6 there, we get 0 at the end, as we should expect, since we knew that -3 was a zero of this polynomial. And then what this allows us to do is to rewrite our function f of x in a kind of broken down, further broken down form. It's not going to be broken down all the way. But we know since -3 is a zero, that the factor x plus 3 is a factor of this function. And when it's divided by that, we get another polynomial whose coefficients will become from the result of our synthetic division. Now note that the highest power, the highest degree on the original function was to the 4th. So we know the highest degree on this new term is going to be to the 3rd. So again, using the coefficients of the numbers we got from our synthetic division, we know that this can be written as 2x to the 3rd minus 5x squared plus 6x minus 2. And then we want to continue searching for zeros from here. Now notice that the function we have here, or this factor we have here, 2x cubed minus 5x squared plus 6x minus 2, we want to find our next zero from that. Unfortunately, though, notice that that is a cubic polynomial. The highest power is 3. It's again, we can't factor anything here because the terms don't all have something in common other than the 1. Some factor by grouping also wouldn't work, since I believe if we factored, let's say, x squared out of 2x cubed minus 5x squared. That would give us 2x minus 5, but factoring a 2 out of the 6x minus 2 would give us 3x minus 1, and unfortunately that's not going to take us anywhere. So we need to figure out a different way to find a 0 of this function, or to break this function down. And to do that, we can just kind of think of that as being like the original function we started with, and we can go ahead and find a 0 the same way. So what we'll do is we'll go back to our graph here on Desmos. Going to clear out the original function. I'm going to put in that new function that we have just found. So 2x cubed minus 5x squared plus 6x minus 2. Okay, and we're going to look for a 0 of this function. And as far as we can see from this view anyways, it appears there's just 1 0 of the function right about there. Looks like it might be at 1/2, but we can again confirm on Desmos. So click on the graph here, scroll down, and we do see that that's at 0.5 comma 0. So we know now that 1/2 is a 0 of that function. And in fact, being a 0 of that function, it's also a 0 of the original function, f of x, that we started with. So let's go ahead and go back to our work here. And we want to continue to break down our function f of x. To do that, we're going to use the new 0 we found for this function, which was x equals 1/2, and perform synthetic division with the coefficients of that function to break down f of x even more. So I'm going to, here in the upper right, put 1/2 in the box now. List out the coefficients of that, which will be 2, -5, +6, and -2. And then just as before, we'll go through and perform our synthetic division. So we'll bring down the 2 here, multiply that by 1/2. You might be a little scared there because we see some fractions now, but 1/2 times 1, you could check in your calculator. You might know that's just 1. Add that to -5, gives us -4. Again, multiply by the 1/2. You can check on your calculator, or maybe you know that would give us -2. 6 minus 2, that gives us a +4, times the 1/2. That gives us a +2. And when that's added to the -2 there, we again get 0 as expected, since we already knew we were starting with the 0 of the function. So good. So now we've broken this down even more. And using this information, we can now rewrite f of x factored even further. So we can write f of x equals, we still have that factor x plus 3 from the first 0 we found. We now know, since 1/2 is a 0, that we can have a factor that is x minus 1/2. And then we can write the remaining factor of the function using these coefficients that we got from our synthetic division, the 2, the -4, and the 4. And to start writing that factor, recall that we started that particular synthetic division with a function that was to the 3rd power. So as we go to rewrite it or break it down some more, we're going to start with the 2nd power. So it's become 2x squared minus 4x plus 4. Okay. And now we've got a function that is a quadratic, and we now know we can continue to break this down or continue to find zeros using our techniques for solving quadratics. Now, before we do that, notice that each of the coefficients here in this factor is divisible by 2. So I'm going to go ahead and do is factor a 2 out of that factor, and when I do that, that can be written out front of that factor. But then, since everything's being multiplied, I'm going to move it out to the very front, just to simplify things. So what this will become is f of x equals, I'm factoring a 2 out of there, so I wrote that in the very front of all of my factors. And then inside the parentheses there, we'll now have x squared minus 2x plus 2 once the 2 is factored out. And again, as I just mentioned, now we'll use techniques for solving quadratics to find zeros of this last factor. So let's go to another slide here. once again, write out the function we're dealing with. So f of x equals 2 times x plus 3 times x minus 1/2. Okay, and then apologize that that's all wonky there. And then here we have the x squared minus 2x plus 2. Now, we might try factoring this last quadratic here, but do note that if we were going to do that, we'd need to find two numbers that add to positive 2, or excuse me, multiply to positive 2 and add to negative 2. We can't get that since the only numbers that multiply to 2 are 1 and 2. And no matter how we put signs in there, we cannot add or subtract those numbers to get negative 2. So this function cannot be factored, or this factor cannot be factored any further. So what we'll do instead is use our friend the quadratic formula, which tells us that to find values of x that make that function equal to 0, we'll do the negative of b plus or minus square root of b squared minus 4ac all over 2a. Remember, the values a, b, and c come from the coefficients in that quadratic. Since there's nothing written in front of the x squared, we assume there's a 1, or imagine there's a 1 there. So now let me fill in all this stuff. So we'll have negative of our value for b, which is negative 2, plus or minus square root of, again, that value for b, which is negative 2 squared, minus 4 times the value for a, which is the 1, times the value for c, which is 2, all divided by 2 times the value for 1, value for a again, which is 1. Go through and do some simplifying. If we do that, the minus and the minus with the 2 here, that gives us positive 2 plus or minus square root. The negative 2 squared here, that's positive 4 minus the negative 4 times 1 times 2, that gives us a negative 8, or minus 8, over 2 times 1 is 2. Simplify some more, so I have 2 plus or minus square root. We have a 4 minus 8 under the root there. That simplifies to minus 4 all over 2. And note this now that what we have is taking the square root of a negative. So that tells us we're going to start dealing with complex numbers here. So I can deal with that by doing 2 plus or minus, introduce I, square root 4 all over 2. Square root of 4 is 2, so this becomes 2 plus or minus, 2i over 2, which breaks down into 2 over 2 plus or minus 2i over 2, which, reducing both of those, gives us 1 plus or minus 1i, or just I. And with that, we find our final two zeros, so the 1 plus I and the 1 minus I. So now, using those together with the factors we have up here, that x plus 3 and x minus 1/2, we finally have our answers here, that the zeros of this function occur where x equals negative 3, x equals positive 1/2, 1 plus I, and 1 minus I. And now we have our answers. And notice that there are 4 of them. And also the degree of the original function was 4. So recall that a polynomial will always have a number of zeros or roots equal to its degree, though that also includes multiplicities. So if any of these roots are repeated, they would still count towards that total degree of the polynomial. All right, that is it for now. Thank you for watching.